2 weeks ago, when we had the last successful lecture, I was giving you an introduction to neural networks. But we'd already covered the distance classifier, and quite a few of you asked for some worked examples of how a distance classifier might work. So today I'll start the lecture by going through a distance classifier example, and then we'll go into the training of a neuron, which follows on from the last lecture I gave you. Right, the distance classifier. We saw three versions. It was the Euclidean distance, the city block distance, and the square distance. And the example I've got, I'm afraid, is 1 week out of date, because what I'm going to try and design is a vote detector for the American election, and to decide whether you or anybody is likely to vote for Trump or Biden. And what we are going to have a 5-element vector. So our input patterns is the input I equals I1, that's a vector, I2, I3, I4, and I5. So that is my vector space, and it's 5 dimensions. Now, 5 dimensions we cannot draw in 2-dimensional space, but the mathematics can be applied to 5D. So I1, what is the information we're collecting? I1, this element here. I1 is going to be age. The age of the person, and we are going to encode it 0 to 10, and we are going to code it in decades. So 0 is under 10, 1 is 10 to 19, right the way up to 10, which will be over 100 years old. I2 is going to be education. And again, we're going to do 0 to 10. And 0 is going to be no qualifications, right the way through to 10. What's it going to be? PhD. I3 is going to be income. Again, the scale 0 to 10, and 0 is going to be no income. And 10 is going to be, what should we say, $500,000 a year. That's I3. I4 is going to be physical health. And again, we're going to have 0 is no health problems. And let's have 10, about to die. And let's have 5, sanity. And again, 0 can be perfectly sane, and 10 can be completely mad. Now, the thing with these scalings is they have got to be linear, so they've got to progress as we go from 0 to 10, increasing, for example, income. 0 is the lowest, 1 will be the next highest, right the way through to 10 would be the maximum. And it's a sort of similar scheme to what you might use if you're filling in questionnaires. And quite often you have a questionnaire to fill in about anything. It could be going from strongly disagree right the way through to totally agree. And again, they can be quantized as numbers. So that is the coding strategy. And from my research 4 years ago, I found a typical Trump voter, and let's call it vector T. And vector T is the vector 2, 3, 4, 7, and 1. That is a 5-dimensional vector. I also found a typical Biden voter. Well, in case it would be Clinton 4 years ago, let's assume they're the same views. And a typical Biden voter would be 9, 7, 6, 7, and 5. So those are my 2 reference patterns for my distance classifier. Keep it simple. We'll just have 1 example per class and assume they're linearly separable. I now discover, or I take a measurement of a complete stranger from the American public, and let's call it vector Y. And vector Y, I find his or her views are going to be rated as 4, 8, 5, 9, and 5. Again, 5-element vectors. And the question is Y a Trump man or woman or a Biden person? Right, now using the Euclidean distance, the equation, remember, is the summation over I equals 1 to D, in this case 5, of Ti minus Bi, the corresponding elements in the reference vectors, squared, and the whole thing is square rooted. And if I perform this equation for Ty, in other words, the distance between the Trump reference and the Y pattern, it is going to be 4 minus 2, let's change color there, 4 minus 2 squared, and that is going to be 4 minus 2 squared is 2, it's going to be 4. Plus from the summation, the next one is going to be 8, or 3 minus 8, and the order doesn't matter because we're squaring. So 3 minus 8 is minus 5 squared is 25. For the third dimension, 5 minus 4 is 1, squared is 1. For the fourth dimension, 9 minus 7 is 2, 2 squared is 4. And for the last fifth dimension, 5 minus 1 is 4, 4 squared is 16. Plus, sorry. Plus 16, which gives a total of 25, 26, 30, 50. Of course, it is the square root, so we should take the square root of the whole of that, and we take the square root of the answer. So Ty, Y has a distance of root 50 from the Trump reference. Now, if we do the same for the Biden reference, it is going to be By, the distance between the Biden reference and the input, is going to be, doing the calculation again, 9 minus 4 is going to be 5, 5 squared is 25. The second element, 7 minus 8 is 1, minus 1 squared is 1. 5 minus 6 is minus 1 squared is 1. 7 minus 9 is 2. 2 squared is going to be 4. And 5 minus 5 is 0, it's going to be plus 0, which gives a distance 25, 26, 27, 31. Of course, it's square rooted. And so taking those two distances, Y is closer to Biden than Trump. So Y belongs to Biden by the distance classifier, by the Euclidean distance classifier. Now, let's take the city block. The city block distance, remember, it is the summation I equals 1 to D over the mod of, let's do the general case, AI minus BI. And if we do that, D Ty for the city block is going to be equal to, going back to the reference patterns, the mod of 2 minus 4 is 2. The mod of 3 minus 8 is 5. The mod of 4 minus 5 is 1. The mod of 7 minus 9 is 2. And the mod of 5 minus 1 is 4. Now, writing those down again, let me jot them down on a piece of paper so I don't forget them. It is going to be 2, 5, 1, 2, 4. Two plus 5 plus 1 plus 2 plus 4. And it's going to give me a distance of 5, 7, 8, 9, 10, 14. Now, repeating the Y pattern from the Biden reference, again going back to the vectors, it is going to be 9 minus 4 is 5. The difference there is 1. The mod of the difference is 1, 2, 0. And so adding those up, it is going to be 5 plus 1 plus 1 plus 2 plus 0. And that is going to be 7, 9. So looking at those distances, the city block classifier, Y is closer to B than T, so Y belongs to class B. Same as the Euclidean. Different measure, it still works. Right, if I now go to the square distance, now the square distance is the maximum operator of I equals 1 to D, again D is 5, of the mod AI minus BI. So we're looking at comparisons between each element, finding the value of the mod between each element and finding which is the biggest. So looking at the vectors, we're doing Ty. The distance between 2 and 4 is 2. The distance between 3 and 8 is 5. The distance between 4 and 5 is 1. Taking the mod, remember, so the sign is always positive. And 2 and 4. The biggest distance is 5. So according to the square distance, Ty equals 5. Now, going back to YB, 4 minus 9 is 5, 7 minus 8 is 1, 6 minus 5 is 1, 7 minus 9 is 2, and 5 minus 5 is 0. The biggest, the maximum value of the mod of pairs of elements is the first one, and it is 5. So BY equals 5. Alarm! The other two distance classifiers give a decision. We are not getting a decision from the square distance. Now, I could have spent 1 hour lecturing on the distance classifier, give you the formula and tell you to remember them, and you could use them. And that's what most people do. They just apply the formulae. But because we've looked at the decision surfaces that occur from these distances, which are different, we find that here these patterns appear to be on the decision surface. And we know with the square distance that the decision surface normally between two patterns is a straight line. That's for the Euclidean. If I apply a approximate distance, if I draw the Euclidean surface in there, the decision surface is likely to be like that. where we get regions of errors where the response will be different depending on the classifier. But we also know, because we've analyzed the behavior of these decision surfaces, that we can have a situation where we have a decision surface which is corresponding to the Euclidean locally, but opens up into a void. This area is the decision surface, and clearly patterns in this region, say there, it would be equidistant between T and B. Whereas if I was using the, perhaps that's a bad position to go, that's a slightly better, more dramatic position. Oh, let's put the pattern up there. Whereas clearly if this was on the Euclidean surface, we would have that pattern there, clearly closer to T and B. So this void is opening out. So in this case, the square distance won't give you an accurate classification. And clearly, one would, if one found this situation, one would say, right, let's try another distance. Let's try the city block, or let's try the Euclidean. Remember, the Euclidean needs much more calculation. So that's the example of a void opening out. Now, if you didn't know about decision surfaces, that would just be a mystery. If that was an exam question, you should be able to explain exactly what's going on. Right, have I got any comments? Oh, my computer's gone down again. Oh.
John, you don't, you can carry on.
I'll carry on. Shout if you have any questions. I haven't got the conversation on my screen at the moment. Right, so that is the distance classifier. And that really is revision from 2 weeks ago, maybe 3 weeks ago. And that could be an example, a typical of an example you might see in some assessment. Right, my screen's now gone. Now what's happened? That's...
Guys, while we are sorting out the screens, can you just give us hands up if you understood material? So I want to see how many of you engaged in the lecture. So we have 37 students, so basically I would expect 37's hands up. If you are not putting hands up, it means you are not listening. Okay, Adam, Amiril, Azim.
How many people are watching this from the slumber of their bed?
Kevin, Rojan, Sahil, Said, Muhammad, Kevin. I don't see you, Kona. George, it's good that you're basically in, but you're not listening. Can I see hands up, everyone, please, before we proceed? Kona, George, Kevin, Muhammad, Prasan, Rojan, Said, Tola. Come on, we are still having some that haven't put the hands up. Guys, can you poke with students who haven't responded yet? So we want to see everyone get engaged. Kona, George, Kevin, Muhammad, Prasan, Rojan. So we can see how many of you are sleeping yet on Monday morning at 11:30. Some more. You haven't expected, yeah? Kona, George, Kevin, Muhammad. Prasan, Rojan. Can we hands up, please? I will mark non-attendance if I don't hear from you guys. Rojan, Prasan, Muhammad, George. Okay, so non-attendance helping. So we still have 4 students. Hands up, please. Kevin, Muhammad, Prasan, Rojan. So we have 4 students who are not active and not listening somewhere else. Thank you, John. You could carry on.
Okay. Thank you. Somebody's watching this from the loo, apparently. How interesting. That's dedication to duty. Okay, just to leave the distance classifier now, you're now in a position, if you're doing surveys, to getting questionnaires from people on their likes and dislikes, to use a distance classifier to match unknown people to the classes that you know about. Now, this could be used for personnel selection. It could be used for advertising. It could be used for classifying any data that can be represented in vector form. And of course, on recruiting, people like Google, if you're applying to Google, they like mavericks. So they might have a profile, a vector of their desired employee, and they may want to employ people who have different views. So in that case, to be not close to the existing personnel vectors might be a good thing. So it's quite a powerful tool for selection. But it does depend on the premise that distance, physical distance in pattern space, is proportional to what we perceive as similarity. And that is not always the case. So beware of the restrictions that imposes. Being close physically to something doesn't necessarily mean it's the same class of pattern. And things like zoom and position for images can throw this method out. Right, now we go back to the neural networks. And the model we developed, the McCulloch and Pitts model, was a device that has an input vector. Let's call it I. This would be I1, I2, and I3. They're your elements. They go through a weight. There is your weight vector, W1, W2, W3. We want to combine those in some way, and the simplest way is to add them together, and we then apply a threshold on the output. Now, if we know the weights, this device is known as a linear discriminator. And I think there's some papers up on Blackboard introducing neural networks, and it has a financial advisor example, whereas you are seeking advice whether to buy or sell a particular investment. And you ask your financial advisor, that could be weight 1, and he says buy very strongly, so that could be +9. You talk to your parents, and they're much more cautious. They are suspicious of it, so their weight would be, say, -3. And you ask your girlfriend or boyfriend, whose financial expertise is impeccable, and they say +5. And if we know those weights, we can get a decision. That is known as a linear discriminator. It implies a linear decision surface in pattern space between the buy and the not buy conditions, and it can be used on any other form of data. Right, the advisors can give different advices. The eyes will change as to what the particular problem is. Now, with neural networks, we don't know the W's. The weight vector. This is the thing that's got to be learned. So we now need a strategy for finding the weight vectors, and this is known as training. And it is based on a thing called Hebbian learning. Which is named after an American called Donald Hebb. And it's a simple strategy. It's common sense, really. It says start off with a weight vector, change the weight vector. If it makes the solution to the problem better or corrects the errors, stick with the new values. If it makes matters worse, discard them and go back to the original. So we make change to reduce error. Right. Now that's a fairly arbitrary strategy. So let's try and get a method which is more rigorous and mathematical to implement this Hebbian learning. So the error method I want to give you is called error correcting feedback. Oh, this writing's getting awful, sorry. Right. The calculation we are doing is a vector calculation, which is w dot I. We are calculating in that model the inner or scalar product of two vectors. This is the model that's doing. There is I, there is w, and what is coming out of here is w dot I. And of course, the method we would use in 2 dimensions would be w mod I cos theta, where theta is the angle between the 2 vectors. That is not available in higher dimensionality. So in higher dimensionality, we use the summation of the product pairs, wi I over all I, which is exactly what this model is calculating. I times w plus I2 times w2 plus I3 times w2. That is the calculation that is being performed in the model. Right, let that scalar product be equal to S, a constant. Now, first condition, if no error, and no error would occur if I belongs to the positive class. And remember, the decision after the threshold is the neuron is either firing, positive, or not firing below the threshold, the negative class. And so if I belongs to the positive class and S is positive, or I belongs to the negative class and S is negative, it's giving the right answer by chance, no change in W. Now, the next condition is if an error and an error will occur if I is the positive class and S is negative, or I belongs to the negative class and S is positive, change the weight vector. Change W. Right. We do this by updating W. So W prime, which is our update, equals the original weight vector plus a fraction of the input pattern that is incorrect. And we do that so that the new weight vector, W prime, dot the current input pattern equals minus S. Before, the scalar product was S. If it was wrong, in other words, if we're getting a positive response, and it should be negative. We make sure that the sign is the scalar product is minus. In other words, it is the same product, but on the opposite side of the decision surface, it will be classifying the pattern correctly. If it's positive, if it's negative class and we want it to be positive, so if S originally was minus, we're now using minus S, minus S will make it plus, and it will get that one correct. Right, so that is our strategy. So let's take the original equation, W dot I, and we substitute for W prime in that equation, which will now give me W prime dot I, which is going to be equal to W plus CI. That is the substituting for W prime, which we've got there, dot I. And that is going to be equal from this equation to minus S. So working on this identity now, let's get rid of the bracketed terms. We're going to have this part is going to be equal to W dot I plus CI dot I equals minus S. But we already know that this is going to be equal to the original scalar product before we updated the weight vector, and that is equal to S. Go back there. W dot I equals S. So we've got S plus CI dot I equals minus S. So that should be an equal sign, shouldn't it? Let's just correct that. Now, tidying this up, put the S over the other side. We're going to have CI dot I equals plus S on that side, put it on the other side, minus 2S. Right. C is the correction factor that we need to update our weight vector. Original weight vector, the current input pattern, the unknown in this equation is C. If we know C, we can update the weight vector. So C is going to be equal to minus 2S over I dot I. So we've got a means of updating the weight vector, which will correct it for the current input pattern, which depends upon S, which was the original error, and the current input pattern. So we can train the network to converge using that update factor, providing, of course, the data is linearly separable, and we'll deal with that later on. Now, that is a useful method for training a single neuron. That is the update equation. But if I were to set this in an exam, under exam conditions, the fraction here is going to become quite complicated because C is going to be, go away. C is going to be dependent on this fraction, and numbers get a little bit difficult. Is there a way we can simplify this to illustrate for simple examples? Well, the answer is yes. And the second method I want to introduce briefly is an approximate method. Now, the approximate method, we're still using the update W prime equals W plus CI. But instead of having a variable correction factor, let C equals plus or minus 1, depending on the sign of the error. So What this means is if S if I belongs to the positive class and S is negative, we've got to make the scalar product of the weight with the input pattern more positive. Let C equal +1. If I belongs to the negative class and S is positive, we want to make the scalar product less positive. Let C equals -1. And that is an approximate method which will converge less efficiently, but it will converge if there is a solution for the problem the neuron is trying to solve. And this is a typical problem that could occur in future assessments. So you need an example, don't you? So the example I want to give you, and again, it should be in the notes on Blackboard, but I'll give it in more detail now. And let's go right the way back to images. And I want to use 4 pixel images. Absolutely trivially simple in terms of image processing, but it will illustrate the method. And I'm going to use 4 pixel images. And I'm going to take 4 training patterns. And supposing the patterns are cross is 1 and a white is 0. And the other class, we can have and those. They hardly have any meaning as they stand, but let's take them as a simple example of 2 categories. And the first thing we have to do is to determine which class is going to be positive or negative. It's purely arbitrary, it could be the other way around, but let's choose this to be plus and this to be minus. We now need the vectors. And to obtain the vectors, right, to obtain the vectors, scanning, remember we start scanning from the top left. Let's call this pattern I1, pattern I2, pattern I3, and pattern I4. The vectors are going to be 1, 1, 0, 1, 1, 0, 1, 1, 1, 1, 1, 0, and 1, 0, 1, 0. Now these are not binary numbers. That is not 13. It is a binary vector 1, 1, 0, 1. So strictly speaking, I should put commas between each of those. And that would be I1. That would be I2. That would be I3. And that would be I4. Right, now let's define the class. And the class we've defined up here. This is positive class. This is a negative class. Now I want to calculate W dot I. Now we need an initial weight vector. So let's choose an initial weight vector of, let's say, 0. It doesn't have to be 0. Any weight vector will do, but that's as good a starting point as any. So that is the initial weight vector. We next calculate the scalar product of that weight vector for let's add another column here. And the next column is going to be C, and the next column is going to be the updated weight vector, W prime. Right. 0, 0, 0, 0, the scalar product with the first pattern is obviously going to be 0. Is it correct? No. We want it to be the positive class, so we want to move the system more towards the positive response. C will therefore be +1. And we now add the input pattern to the weight vector. Remember, W prime is W plus Ci, and C is +1. We will add these vectorial. Our updated weight vector will be 0 plus 1 is 1. 0 plus 1 is 1. 0 plus 0 is 0. And 0 plus 1 is 1. Obviously, it's the same as the input pattern because we're adding nothing to it. This now becomes our new weight vector. We've changed it. We now use this for the next scalar product. And so we're now taking the scalar of the updated weight vector with I2. And it is going to be 1 times 1 is 1, plus 1 times 0 is 0, plus 0 times 1 is 0, plus 1 times 1 is 1. I think it's going to be +2. Positive, it is correct. No action required. So the change on the first pattern, we're getting the second pattern correct. Now, the negative class. Latest weight vector, 1, 1, 0, 1. The scalar product with this pattern is going to be 1 plus 1 plus 0 plus 0. It's going to be +2. Wrong! It should be negative. We need C to be -1. We now subtract the current input pattern from the latest weight vector. It will be 1. Let's give you the link there. 1 minus 1 is 0. 1 minus 1 is 0. 1 0 minus 1 is -1. And 1 minus 0 is 0. Have I got that correct? 1 minus 0, 1 is 0. 1 minus 1 is 0. 0 minus 1 is -1. And it should be +1, shouldn't it? Yes. Right, we've changed the weight vector. Final pattern from the training. Scalar product of the latest weight vector with this is going to be 0, 0, -1, 0. -1. It is correct. No change. And that sounds like a simple training strategy.
John, we have a question.
Yes.
How is that last bit +1?
Have I made a mistake?
No. Can you please clarify who was asking a question? I don't see. Zachary, please clarify.
I've lost my conversations. Now the computer's gone down.
It was just the 0, 0, -1 +1.
Right. What we are doing is we are doing W prime dot I. And it's going to be this W prime and it's going to be I4. The scalar product is 1, or the weight vector 0 times 1 is 0. So it's going to be equal to 0. For the next element, it is going to be 0 minus 0 times 0 is 0. For the next one, it is going to be minus 1 times 1 is minus 1. And for the last one, it is going to be 1 times 0 is 0.
It was more how you got +1 at the end.
The +1 at the end. Go away. Right. I've most probably made a mistake here. It is 0, 0, minus 1. It should be 0. You're correct. You are quite correct. Sorry about that. Correction, folks. That should be 0.
I don't get it. Why should it be not?
Because you are multiplying.
Ah, you're multiplying. Oh, okay.
Multiplying. You're multiplying.
Got it. Thanks.
It's summation WI, II. That's what you're calculating. Okay? Right, folks. Something crucially important is now emerging. Well, let's rub that out. We've got to the end of the training. We've got a weight vector, and the weight vector was 0, 0, minus 1, 0. We have made changes in the training. The weight vector has changed as it goes through the iteration. It's getting new patterns correct, but because we're changing the weight vector, we are moving the decision surface, which will be a hypersurface in 4-dimensional space. It might get previously correct patterns wrong. So this leads to a huge disadvantage of this method. Let's erase that. Oh, where's that gone? You have to repeat the training. If a change has been made in the weight vector, you need to repeat training. And that leads us to the second iteration of the training. Let's keep that in so I can see the... And the input patterns are going to be I1 is going to be 1, 1, 0, 1. I2 is going to be 1, 0, 1, 1. I3 is going to be 1, 1, 1, 0. And I4 is going to be 1, 0, 1, 0. The class again is plus, plus, minus, minus, same as before. Right. We've now got the latest weight vector. So after the first iteration, W was equal to 0, 0, minus 1, 0. Repeat the scalar product of the latest weight vector.
I'm sorry, John.
0, yes.
Shouldn't I4 be 1, 0, 1, 0 at the bottom?
0, 0, minus 1, 0. Okay.
Okay.
Right, scalar now. 0, 0, minus 0, 0. It is giving a scalar product of 0. It is wrong. We need for positive class C to be, remember this is correct. This one is going to be C. C has to be plus 1. We now add it up. This is the W prime again. Add this pattern now to the current weight vector. It gives me 1, 1, sorry, 0, 0. Naught minus 1. Right. Scalar product with the next pattern. 0, 0, 0, 0, minus 1. It is wrong. Update the weight vector again. Add this to the weight vector. It is going to give me 1, 0, 1, 0. Scalar product with I3 is going to be 1, 0, 1. What's going to be plus 2? That is wrong. C is going to be minus 1. We need it to be the negative class. Subtract this from the current weight vector. It is going to be 0, 0. Sorry, oh dear. It is going to be 0, minus 1. Minus 1, 0, 0. And the final one is going to be scalar product of the latest weight vector, 0.
John, I4 should be 1, 0, 1, 0.
Oh, dearie me. Thank you. Right. How are we doing now? Scalar product, 0, 0, 1, 0, plus 1. Should be the negative class. Subtract I4 from the current weight vector. The update is going to be 0, 0. It goes to 0. Something has gone wrong somewhere, folks. Where have I made a mistake?
Yeah, what I asked before was why is it multiplying, but it was not multiplying. You had it correct.
Hang on, I've got my notes out here. Let's go back to the first one. 1, 1, 0, 1 is correct. It remains the same. This should be a minus 1 according to my notes. Now, why have I got a plus 1? Let's check this. So the input pattern is 1, 1, 1, 0. The latest weight, the weight vector was 1, 1, 0, 1. It needs to be negative. So we subtract I3 from the weight vector. It is going to be 0, 0, minus 1, plus 1. That should be plus 1.
Yeah.
Yes. Right. We're getting there. Plus 1. Now that remains correct for the other two, according to my notes. So what we should be carrying over from the first iteration, that should be plus 1. Right, now, what mistakes have we got in here? The scalar product of the latest weight vector with the current input pattern is going to be, oh, go away. Is going to be 0, 0, 0, 1, plus 1. Agreed?
Yes.
Thank you. Right, the latest one with the second pattern is going to be 0, 0, 0. Sorry, I'm adding 1, 0, we're adding
the scalar product for I1 should it be 0?
For I1,
yeah,
it is 0. It's got to be positive, so we're adding. So we're adding this. It is going to be, oh goodness me.
I can't lie, we've got a lecture now.
Hey, I've run out of time. Sorry about that, folks. I'll pick up from here this week, next week. The method is in the notes on Blackboard. Go through it yourself and we'll try and sort it out next week. It's quite simple if you get the figures right. I'll try and sort it out for you for next week. Okay, guys. Hopefully you've got a bit more information than we had last week. I better close now.